Okay, guys, so this is Discrete Optimization, linear programming, okay? And this is part 4, okay? So this is going to be a transition lecture, okay, between the basic, simplex algorithm and duality theory, which is this beautiful, marvelous things that you need absolutely to know about, okay? This is essentially introducing a bunch of notations, okay, of what we have seen already, proving some of the results we saw without proof before, using that notation so that you get familiar with yourself, and then introducing this tableau, okay, which is really a very useful tool when you actually implement the simplex algorithm or you do things by hand to actually understand them better, okay? So this is a lot of notations today. I'm trying to make it easy for you, but this is also very useful if you start reading papers, if you start reading books. You need to understand some of these notation, okay? It's all trivial, but it's kind of boring, right? And it's kind of confusing. So this is essentially a system of linear equations, okay? And one of the things that we need to do when we talk about matrix notation or the tableau is to actually view this as a big matrix, okay? So essentially what you see here, you have all the coefficients of all these variables. You can view them as a matrix, right? So first column, second column, third column, and so on. So there are as many columns as there are variables. There are as many rows as there are constraints. And these guys are going to be the right-hand side. We're going to see that, as well inside the tableau at some point. Okay, so typically what we do when we are doing the simplex algorithm is that we have a basis. These are going to be the basic variables. The other ones are going to be the non-basic variables. All this you have seen, master, you love this thing, hopefully. So the basis here is variable 3, 4, and 5. Sometimes we're going to call this guy the matrix there the basis as well. This is kind of abusing notation or language. Okay? So remember, in most of the other lecture, what we were doing is basically taking the basic variable, isolating them. They become part of the left side. Okay? They are expressed in terms of the constant, and then the rest of the non-basic variables. Okay? And so that's what we did. Okay? So once again, you can view this thing here as a matrix. It's part of the big matrix here, okay, once we do some operation on it. And this is kind of also a part of the matrix, but which is very nice, it's like a diagonal matrix, okay? So I'm going to show you that in detail, okay? So essentially, you can re-express the whole thing here in terms of basically two matrices, okay? And then some, vectors, column vectors, okay, for the basic variables and the non-basic variables, okay? So the basis is always going to be, so let's forget. So this basis here is a very nice form, but it's not always going to be the cases. But let's say this is the part of the matrix associated with the basic variables. You see the basic variables over there. This is essentially the part of the matrix which is associated with that. Okay. In this particular case, is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. And then the rest here is the part of the matrix when you see this big thing over there, right? Associated with the non-basic variable. Okay, which is x1, x2, and then x6 over there. Okay, so you see the first basic variables there. The first non-basic variable there, x1, it has a column which is 3 to 1, and that's the column that you see here, right? So 3 to 1. Then you see the next variable there, x2, okay? So the column is 1, 0, 0, okay? This is the column that you see there, 1, 0, 0, okay? And then finally, you have the column for x6, which is basically 0, 1, 1, okay? And you see 0, 1, 1 there. I mean, you see it, I don't see it. I can tell you the screen that I'm looking there is so tiny and it's reversed. There is no way I can see anything. So, but this is very interesting, exciting, right? And then you see the right column there, which is basically the coefficients that you see there. Okay? So this is basically the matrix notation. And then we're going to use some, nice algebraic notation for, representing this. This is A subscripted by B because this is associating with the basic variable, xb, the basic variable. This is an, that's the part of the big matrix which is associated with the non-basic variable. These are the basic variables and this is B. Okay? So once again, the formula that I'm always going to tell you is that we have what? AB, okay, times xb plus an times xn, okay, is equal to B. Okay, so this is basically reformulating this entire system of equation as a formula about, with matrix notation. Okay, so in a sense, everything that I told you last time can be summarized in this particular form. Okay, so we have a system of equation AX is equal to B. Okay, now I have to find a basic feasible solution. How do I do that? I take a set of linearly independent column in the matrix A. Okay, these columns are called AB. These are the columns of the basic variables. And then I start re-expressing these basic variables in terms of the non-basic variables. So I have these first constraints that I've just described on the previous slides, right? AB times XB plus AN times XN is equal to B, okay? Now I want to isolate the basic variables, okay? So I have AX, AB, XB on the left-hand side. And on the right-hand side, what do I get? I get B minus AN times XN, okay? So once again, basic variable, non-basic variable. I still have a matrix there, okay? So if it's not, the nice diagonal matrix, unit diagonal matrix, I have to basically get rid of it. So I basically compute it inverse, multiply, the inverse by the matrix itself, which is basically the diagonal matrix that I wanted. But then on the right-hand side, you see basically the inverse of the basis. AB minus 1 times B this time, and then you see AB minus 1 times AN times XN. Okay, and this basically give you the expression of the basic variables in terms of the non-basic variables. Okay, now when we do these operations, in the equations before, what we get is we get a new set of right-hand side B prime, which is equal to this AB minus 1 times B. Okay, that's what you have there. And then you get new coefficients for the non-basic variables, which, I'm calling here AN prime, which is basically that subset of the matrix which is associated with the non-basic variable. Okay, so this is essentially a basic solution, right? And it's going to be feasible if all the B primes are greater than 0. So this is how I compute a basic feasible solution, right? So I'll select this, M linearly independent column. I'm re-expressing the basic variables in terms of the other one, and I'm testing feasibility here, right? So same thing as we have seen in the previous lecture, but just in matrix notation, okay? Now, the matrix AB is also called a basis. As I told you, we call basis a lot of things, okay? So in a sense, linear programming, okay? So this is the statement of the problem. You minimize Cx, with the constraints Ax equals B, okay? And then you get this basic feasible solution here, which express XB in terms of the non-basic variable using this matrix notation, inverse of the basis times B minus, inverse of the basis times AN XN, okay? And now one of the things that you may ask is, what is the cost? Because I haven't covered the cost yet. But the cost we can express in exactly the same fashion, right? So we can say that Cx is equal to what? Cb times, xb, so these are the basic variables, and then Cn times xn, which are the non-basic variables. Of course, once you have that, well, we know the value of the xb, the basic variables, so we can re-express them in terms of this equation, and that's what I'm going to do in the next equation. Okay, so take a deep breath, because that's going to be ugly formula, okay, but very simple. So what we know is that we want to compute Cx, okay? So you have Cx times xb plus Cn times xn, okay? Now we know the value of xb. This is this ugly, inverse of the basis times b minus inverse of the basis times an times, xn, okay? And that's what we just did here, okay? So we just substituted inside for the value of xb, okay? So you see this is the second equation, okay? Now I invite you to look at the third equation, which is basically a simple distribution, simple algebraic manipulation there, such that I can isolate, the constant term and then the term which is only associated with the variable, the non-basic variables. Now the next line, actually the next two lines, so what we do here is interesting, right? So when you look at what we have done so far, you see this expression which is multiplying the non-basic variables. So essentially this expression is in terms of the non-basic variable using also the notation Cn and An, which is part of the matrix which are used only for the non-basic variables. What I would like is to have this expression but re-expressed in terms of the overall matrix, and that's what I'm going to do in the next two lines. Okay, the first thing that I do is that I'm saying, okay, so this is about Cn and An. I want to have the same kind of relationship, but for the Cb's and the Ab's, okay? Because if I do that, then I can merge the Cb and the Cn, the An and the Ab. I have the global matrix and the global cost. And that's what I'm doing here. I'm adding a term for the Cb's, okay? And this term is essentially 0. Why? Because I have Cb over here, okay? And then I have Cb times the inverse of the basis times Ab, okay? Now, the inverse of the basis, times the basis, that's going to be the diagonal matrix. So what I get here is basically a CB minus CB, which is 0. Okay, so this is why this term is 0. But now when I basically re-express these two terms together, I get this beautiful, really beautiful, truly beautiful expression, which is what? Which is C, no basic variables, no non-basic variables, the entire coefficient, the row of coefficients. Okay, and then I get what? CB here, times AB minus 1, okay, and then I have the real matrix A, right? So in a sense, the only thing here which depends on the basis are basically this expression in the middle, and this is actually very important, and you'll see why. But the C here is a real, doesn't depend on the basic or non-basic variables, and you have the real matrix A, okay? So this is essentially how you can re-express Cx. Cx is equal to this expression, where you have the value of the constant there, and then you have basically the non-basic variables over there, which are expressed in terms of C and then A and then these things, okay? And this thing, we're going to denote them pi, okay? And these pi's are very important, okay? You'll see them all over in the next two lectures. They're called the simplex multipliers, okay? And so pi is equal what? Is equal to CB times the inverse of the basis, okay? Now, sometimes I'm going to say P because pi in Greek is P, and I'm going to be confused, but, I'm trying to say pi all the time, but in Greek it's P, so I'm confused, all right? But this simplex multiplier had this value, which is very important. It's CB times the inverse of the basis. Okay? Now, so this cost here, Cx, okay, I can re-express, now in terms of these simplex multipliers as simply pi b minus C minus pi a times x. Okay? So this equality is very nice because now it's only expressed in terms of these simplex multipliers, and it becomes this beautiful thing, C minus pi, so C minus pi a over there. And this is very important. Why is it very important? Because at optimality, we know that we have a property on these guys, right? What is the property? Do you remember that beautiful property? These guys have to be greater or equal to 0, okay? So the relation here, C minus P A has to be non-negative. Okay, so this is what I'm basically trying to do. So this thing here is the same as that. Expressing the simplex multiplier, I know that C has to be greater or equal to pi a. Okay, so which is essentially equivalent to this because pi is equal to CB times the inverse of the basis. Okay, now once you have that, this is very interesting. Okay, so I know that the basis is optimal if these costs are non-negative, and I have this relationship between C and pi a. Okay, and once I have that, I can very easily prove now that at optimality, these costs have to be greater than 0. Okay, so let's denote C star. Okay, you see C star. Okay, C star is equal C minus pi a. Okay, and I also have C0 star, which is the value of pi b, which is like CB times the inverse of the basis times b. And so this is the value of the objective function at optimality, right? So what I need to prove is that these guys, so that at the solution where C is greater than pi a is an optimal solution. I need to prove that, okay? So what am I going to do? I know that I believe I have detect optimality, which is the property that C is greater than pi a, okay? And that's what you see there. And now what I'm going to do is that I'm going to take another arbitrary feasible solution y, and I'm going to show you that the cost of y, the objective function for that basic feasible solution, okay, is going to be greater than C0 star. Okay? If I show you that, it basically means that when I get to a particular basic feasible solution where C is greater than pi a, then I know that I'm at the optimal solution. And how do I do that? It's very simple at this point. Okay, so what do I know about y? I know that it has to be a feasible solution, right? So what I know is that it has to satisfy this constraint, which is ay is equal to b. Okay, and then I just have to do the following manipulation. Okay, so I have to find a cost cy, right? So that's the cost of the feasible solution y. Okay, now I know because I'm basically detecting this property, right? That C is greater than pi a. So I can replace this C by pi a, and so Cy is going to be greater than pi a times y. Okay. Now you look at this expression here. It's nice, right? So it's pi a y. But what do I know about y? I know that y has to satisfy this condition. So pi y has to be equal to b, okay? So I get essentially the value pi b, and pi b is the value of the solutions at that basis when this condition is satisfied. So this is the optimal solution, because essentially any other feasible solution is going to be greater than that. So what I'm basically showing you here with matrix notation is that every time I detect that this property is, satisfied, the cost in the objective function are all positive now, I'm basically optimal. Okay? So that's why this matrix notation is useful. Some of these properties are easier to state. Okay? Now the other things that I need to tell you, and this is really important, is the tableau. Okay? So a lot of the papers, a lot of the books that you're going to read are going to work with this tableau. And essentially this tableau is going to put everything together in the right hand side, the left hand side, all this, the basis, everything in one big matrix. Okay? One big array. Okay, so we're going to put all these coefficients, we're going to put all these coefficients of the objective function, all the coefficients of the matrix here, the right-hand side, all these things are going to be in one big tableau. And then you can do pivoting or simple naive implementation of the simplex algorithm very easily with one big matrix. Of course, practical implementation don't do that. They are much, they are much more efficient representation, because most of the time this matrix is sparse and you want to, exploit that sparsity. But this is the tableau, okay? And this is how you can actually compute these things, by hand or simple implementation. Okay, so this is essentially the system of equations that I've shown you, and this is the first basic feasible solution that I'm showing you for that particular system. Okay, and so what I want to show you is that we have the basis, we're going to have the right-hand side, we're going to have we're going to have the objective function represented there. Okay, there are some convention, and some of them may not be natural, but these are the convention that most people are using. Okay, so what you see there, the first row here is going to be the negation of the objective value. Okay, so the way to think about this in terms of what we have done before is like exactly, when we were looking at the objective function, that's what was on the right hand side, except the value here, which is going to be negated. Okay, the constant is going to be negated. But all these guys, think of them, they were on the right hand side of of the formulation that we have that we were using when we were doing the representation where the basic variables were isolated from the non-basic variable. What you see there, you see the basic variables, the basis, okay, and the basic variable is always going to be a nice matrix, 1 0 0 0 0 1 0 0 0 0, 1, 0, 0, 0, 1. That matrix can be anywhere. It's going to move, right? And it doesn't have to be in that order. But somewhere, there will be these basic variables with 1, 0, 0, 0, 1, 0, and 0, 0, 1. And of course, you can generalize that. Okay? And then you see the right-hand side over there. These are the B values that you see over there. Okay? So basically, this is the basic feasible representation expressed by the tableau. So you see the basic variables there. Okay? So they are one, they are there. The other ones are like what we have seen before, but we brought them, in a sense, you have to think about them. We brought them to the left side. Okay? And so the coefficients that they have are the negation of the coefficients when we were represented that as a set of equations. Okay? So instead of having a 2, you have a -2. Instead of having a -3, you get a 3. Okay? So this is basically, the tableau representation. Okay? So we look again at this tableau representation and assume that we are doing the simplex algorithm on top of this one. Okay? So what we are going to do is we're going to look at basically the objective function. And once again, if all the values there are strictly positive, okay, or greater or are non-negative, okay, we will be at optimality. In this particular case, it's not the case. Okay, so you can see that we have a -3 and -3 over there. And so that basically means that these two variables want to enter the basis. Okay, they say, oh, I want to go into the basis. Okay, and so we can actually, select a variable to enter the basis. And now we left to select a variable to leave the basis. And once again, remember, we flip the sides of these non-basic variables. So before we were looking at variables with a negative coefficient. Since we flip them, from one side to the other, in this particular case, we have to look with values that are positive. So for this particular guys, we're going to look at the first equation. We're going to look at the last one. These are the two equations that we can select. We're going to compute the ratio between that coefficients and the value b. In the first case, it's going to be 1/2. In the second case, it's going to be 1. So the variable, the constraints that we are going to use to pivot is going to be the first constraints. We're going to do the pivoting operation, and this is the resulting tableau. Okay? So once again, what you're going to see is the objective function in the top row. Okay? And now, the nice thing is that you see these guys, they are strictly positive, which basically means that we are at optimality. Okay? And these are the values of the non-basic variables. Okay? So now, once again, you see the tableau there. You see the variable x2 there, 1, 0, 0, that's part of the basis. You see 0, 1, 0, and then you see 0, 0, 1. Okay, this is the basis. You see that some of the columns of this basis are now interleaved with some of the columns of the non-basic variables. Okay, and obviously you see the value of the non-basic variables. Okay, x2 now is equal to 3.5. X4 somewhere here is equal to 7.5, and so on. Okay, and the value of the objective function at this point can be found in this column, and it can be found in this column, and its value here is minus 9.5, which means that the real, but this is minus the objective function, so this is going to be 4.5. Okay, so this is what the tableau does. Okay, basically the same information that we have seen before, but it's kind of put in one big matrix with various convention. Okay. So this is essentially this transition lecture. So I'm done. So I've shown you how actually we could use this matrix notation. It's very convenient in general, okay, once you get used to it. And the tableau is also something that is very nice, and we'll be able to express some beautiful property just reasoning about this tableau later on. Okay, so thank you very much.